next thing we're going to do is we talk about the transform of derivatives. Right? The idea is that we want to transform the differential equations in the time domain to an algebraic equations in the frequency domain. Then we're going to apply the inverse Laplace transform to turn or to transform functions in the algebraic domain to the function in the time domain again. Okay. And all of this transform of derivatives can be shown using definitions of Laplace transform. I'm not going to prove that. I'm not going to show you the details. I'm just going to give you the formula so that just get the answer. All right. So the Laplace transform of the first derivative, so f prime of t, Laplace transform of f prime of t is going to be s times Laplace transform of f of t minus f of 0. So f of 0 can be thought as the initial conditions or the evaluations of the function at time t equals to 0. There's a quick notations. You see that in the last lecture or in this lecture as well. That is the Laplace transform of f of t. If you convert that into the frequency domain, you have the notations of capital F of s. So for this formula, not only you can write the Laplace transform of f of t, or you can write this as times capital F of s minus f of 0. So capital F of s, right, the capital letter is the transform of the little f function. So that's the first derivative. Now for the second derivative, you have Laplace transform of f double prime of t is equal to s squared times Laplace transform of f of t minus s times f0 minus f prime 0. Right. For f0 and f prime 0 are initial conditions. Because we are working with second order differential equations, then you require to have two initial conditions. Now, when you move to the third order differential equations, then it requires you to have three initial conditions, so on and so forth. And similar to the last case, when you have Laplace transform of f of t, you can write that as, so this is s squared times capital F of s minus s times f of 0 minus f prime of 0. And when you in the initial value problem, the one that you're looking for is the value of capital F of s. Okay, and that is the function in the frequency domain. And in general, the Laplace transform of the nth derivative or the n order differential equations, when you deal with that, is going to be Laplace transform of f and t, stand for the nth derivative of the function f, is going to be s to the power n times Laplace transform of f of t minus s to the power n minus 1 times f of 0 minus s to the power n minus 2 times f prime of 0 minus dot 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 up to. So you keep doing this, right? F of 0 you multiply with s to the power n minus 1 for whatever n is. It depends on the order of the derivative. Then you're going down to, so you have s to the power n minus 2 times f prime of 0, so on and so forth. And you go down to s times f n minus 2 of 0. So this is to the n minus 2 derivative. And then the last one is f to the n minus 1 derivative. And for shorter notations, you have Laplace transform of f of t is capital F of s minus s to the power n minus 1 times f of 0 minus s to the n minus 2 to f prime of 0 . All right. So for this particular lecture notes, we only focus on the second order differential equations. We're not going to go crazy. We're not going to go to the third order differential equations or the fourth order differential equations. That's maybe for another class. I just want to illustrate to you how Laplace transform and inverse Laplace transform can be applied to the second order differential equations to get the solutions compared to ultimate coefficients or variations of parameter. Okay, or even for the method of the characteristic. So that is Laplace transform of some derivatives. Right? Now we're going to move on to example where we want to apply Laplace transform and inverse Laplace transform to find the solutions of the second order linear or non-homogeneous with constant coefficients. Right? Okay, so given this initial value problem where the differential equation is y double prime minus y prime minus 2y equal to 0, and the initial conditions of y of 0 equal to 1 and y prime of 0 equal to 0. We want to use Laplace transform to transform this initial value problem to an algebraic equations. We'll see that. Alright, so first thing first, we're going to apply Laplace transform on both sides of the equations, of the differential equations. So you have Laplace transform of y double prime minus y prime minus 2y equal to Laplace transform of 0. So Laplace transform of 0 is just 0. Laplace transform of the left-hand side, you can apply the linear operators properties on Laplace transform. That is, you're going to have Laplace transform of y double prime minus Laplace transform of y prime minus 2 times Laplace transform of y equal to 0. And Laplace transform of y double prime is going to be s squared times Laplace transform of y minus f times f of 0 minus f prime of 0. Then minus Laplace transform of the first derivative, that is s times Laplace transform of y minus f of 0. So in this case, sorry, it's y. So let me switch that to y. So s times y of 0. This one is y prime of 0. And this one is y of 0. Okay. And then at the end, you have minus 2 times Laplace transform of y. So minus 2 times Laplace transform of y equal to 0. Okay. Now instead of keep writing L of curly brackets, I'm going to switch that to capital Y of S to indicate that this is the Laplace transform of the function y in the frequency domain. Okay. So I have s squared times capital Y of S minus s times y of 0 minus y prime of 0 minus s times capital Y of S plus y of 0 minus 2 times capital Y of S equal to 0. The next step is to substitute the initial conditions into the equations. Right? So y of 0 is equal to 1 and y prime of 0 is equal to 0. So y prime of 0 equal to 0. Y of 0 is equal to 1. Y of 0 is equal to 1. Therefore, you have s squared times capital Y of S minus s times y of S plus 1 minus 2 times y of S equal to 0. Now again, what you're looking for is you try to solve for y of S. So you take capital Y of S as a common factor. You're left with s squared minus s minus 2, then minus s plus 1 equal to 0. Then still you're going to solve for capital Y of S. You move these two terms, negative s plus 1 to the right hand side, and here you get capital Y of S times s squared minus s minus 2 equal to s minus 1. Right. And when you divide both sides for s squared minus s minus 2, you have capital Y of S equal to s minus 1 over s squared minus s minus 2. And in the denominator, you can factor the quadratic expressions, and you get s minus 1 over s minus 2 times s plus 1. Okay. That is, you have the initial value problem originally, right? It's in time domain. Now you use Laplace transform and you transform that to a function in a frequency domain, right? And here, if you want to find the solutions, you're going to use inverse Laplace transform, and then you get to turn the function in the frequency domain back to a function in a time domain. Okay. So the whole process you got here, that when you use Laplace transform, you transform a differential equation or the initial value problem in the time domain to an algebraic equations. Right? So this is an algebraic equations in the frequency domain, and you solve the solutions in the frequency domain. Okay. And with this solution in the frequency domain, if you want to find the solution in the time domain, you apply the inverse Laplace transform. And that is example 6. Right? So to find the inverse Laplace transform, to find the solutions, you apply the inverse Laplace transform. So y of t is equal to the inverse Laplace transform of capital Y of S, or the inverse Laplace transform of s minus 1 over s minus 2 times s plus 1. And for this particular problem, we already did that in example 4. So we go all the way up here, and we have the solutions process of finding the inverse Laplace transform of this fractions. Right? So that is example number 6. And the solutions you get is that 2/3 times e to the negative t and plus 1/3 times e to the 2t. So the solutions here is from 2/3 times e to the negative t plus 1/3 times e to the 2t. Okay, and this is from example 4. Right. So that's the whole process, right? To find the solutions of initial value problem using Laplace transform and inverse Laplace transform. So steps, like the procedure is that you apply Laplace transform on differential equations, then plug in the information for the initial conditions, then you get a function or solutions in the frequency domain. Then you use inverse Laplace transform to turn the solution in the frequency domain to a solutions in the time domain. So right here again is y of t, the solutions in the time domain. That is exactly what you're looking for. Okay, let's move on to number 7. Very similar problem. You have the initial value problems, and you can do this. You can solve the solution using Laplace transform. So this initial value problem is easy enough that you can just use method of characteristic to solve for the solutions of the non-homogeneous differential equations. Right? But for this problem, we're going to use Laplace transform and then later inverse Laplace transform to find solutions. So the Laplace transform of this differential equations is going to be that the right hand side is equal to 0. For the left hand side, you apply the linear properties of Laplace transform to rewrite the equations or to rewrite the expressions. So Laplace transform of x double prime minus Laplace transform of x prime minus 6 times Laplace transform of x equal to 0. Then apply the formula for Laplace transform of derivatives. So you get s times Laplace transform of x minus, sorry, this is s squared, minus s times x of 0 minus x prime of 0 minus s times Laplace transform of x minus x of 0 minus 6 times Laplace transform of x equal to 0. So Laplace transform of x, instead of writing that, we're going to write capital X of s, and then substitute the value of the initial conditions. So x of 0 equal to 2 and x prime of 0 is equal to negative 1. So here you have s squared times capital X of s minus s times x of 0, which is 2, minus x prime of 0, which is negative 1, minus s times capital X of s plus x of 0, which is 2, minus 6 times capital X of s equal to 0. Then you want to simplify, combine like terms, and see what you get for capital X of s. So take capital X of s on the left hand side as a common factor. You left with s squared minus s minus 6 and minus 2s plus 3 equal to 0. So this is negative minus negative 1, which is positive 1 plus 2 is 3. And then you solve for capital X of s. S squared minus s minus 6 equal to 2s minus 3. And then capital X of s equal to 2s minus 3 altogether divided by s squared minus s minus 6. So that is the solutions in the frequency domain. And for the denominator, you can actually factor it into a product of two factors, right? S minus 3 and s plus 2, right? And which is the linear factor. So capital. So this one you can factor the denominator, and you get 2s minus 3 divided by s minus 3 times s plus 2. Okay. Any questions so far?
No, but could you like move it so I can see the beginning of the problem a little bit?
The which one?
Oh, there it is. No, never mind. Yeah, thank you.
Okay. Okay. So now the next step is to solve the solutions, right, in the time domain. So to find the solutions, the solutions. Accept t in the time domain. We use the inverse Laplace transform on capital X of S. That is, you have X of t equal to the inverse Laplace transform of capital X of S. Well, this is the inverse Laplace transform of 2s minus 3 divided by s minus 3 times s plus 2. And similar to the last example, what you're going to do is you're going to apply the partial fraction decompositions to separate this fraction into two smaller fractions. Okay, and from there you can apply the inverse Laplace transform a little bit easier. So we're going to consider 2s minus 3 divided by s minus 3 times s plus 2. Now you're going to separate this into two smaller fractions, and in the denominator of this fraction you have two linear terms, and therefore what the composition is going to be a over s minus 3 plus b over s plus 2. So let me quickly note that this is partial fraction decompositions. The next step is to combine the two fractions on the right-hand side. When you find the common denominator, you have 2s minus 3 divided by s minus 3 times s plus 2. So this is equal to a times s plus 2 plus b times s minus 3 altogether divided by s minus 3 times s plus 2. Now the denominators is the same, right? So we just match the numerators together. So you got 2s minus 3 equal to a times s plus 2 plus b times s minus 3. Then you have to solve for a and b. Right? So if or when a equal to negative 2, you got 2 times negative 2 minus 3 equal to a times negative 2 plus 2 plus b times negative 2 minus 3. The left-hand side of this calculation is negative 7 equal to negative 5 times b, because this term is 0 already. And therefore, b is equal to 7 over 5. Now, similarly, when, this one, I need to change this one. So instead of a equal to negative 2, s equal to negative 2. And when s equal to positive 3, you got 2 times positive 3 minus 3 equal to a times 3 plus 2 plus b times 3 minus 3. This one is 0, then you can find the value of capital A. So this is 3, this is 5a, and therefore a is equal to 3 over 5. Alright, so far so good? Okay.
Yep.
Alright, so now from the big fractions, you're going to be able to separate them into two smaller fractions, right, using partial fraction decompositions. Then the solution is going to be, so x of t is equal to the inverse Laplace transform of, now you have two smaller fractions, that is 3 over 5 times, so 3 over 5 times 1 over s minus 3 plus 7 over 5 times 1 over s plus 2. And at this step, we can use the linearity properties of the inverse Laplace transform to separate this even further. That is, you can rewrite this as 3 over 5 times the inverse Laplace transform of 1 over s minus 3 plus 7 over 5 times the inverse Laplace transform of 1 over s plus 2. And then, in order to find the inverse Laplace transform, of course, what you do is you go to the table of Laplace transform and look for the 1 over s minus 3, right, or something similar. Okay, so let me go to the Laplace transform table. So you go to here for this formula, so number 15. So the one that you got is 1 over s minus 3. So you have 1 over s minus 3 So we just mimic this formula, 1 over s minus a, for a is equal to 3 in this case. So one thing, the inverse Laplace transform of 1 over s minus 3 is e to the 3t. And then the second equation that you're looking for is inverse Laplace transform of 1 over s plus 2. So 1 over s plus 2. You want to have a subtractions in the denominator, so you can rewrite this as 1 over s minus negative 2. Right? But in this case, a is equal to negative 2. So the second solution you got is e to the negative 2t. So let me go back to the notes. So here, the inverse Laplace transform of 1 over s minus 3 is going to be e to the 3t, and the inverse Laplace transform of 1 over s plus 2 is e to the negative 2t. So you get 3/2 times e to the 3t plus 7 over 5 times 3 over 5 times e to the 3t plus 7 over 5 times e to the negative 2t. And that's how you get the solutions of the initial value problem using Laplace transform and inverse Laplace transform. Okay. Hopefully you followed the procedure. Please let me know if you have any questions on this, okay? Then I'm going to move on to one last example here. This is going to be the initial value problem of the second order differential equation with no homogeneous right hand side. Right? In this case is psi of 2t. So you want to find the solutions of this differential equation satisfying the initial conditions of y of 0 equal to 0 and y prime 0 equal to 0 using Laplace transform and inverse Laplace transform. Nice. So similar to the last two examples, what you do is you apply Laplace transform on both sides of these equations, and you get Laplace transform of y double prime plus y equal to Laplace transform of psi of 2t. Now, what is Laplace transform of psi of 2t? So you go to Laplace transform table, and you go to this equations right here. So psi of 2t, in this case b is equal to 2, so Laplace transform of psi of 2t is 2 over s squared plus 2 squared. So Laplace transform of 2t is 2 over s squared plus 2 squared, which is 4. Alright. Now on the left hand side you have Laplace transform of the sum is the sum of Laplace transforms. So Laplace transform of y double prime plus Laplace transform of y equal to the right hand side, which is 2 over s squared plus 4. Now Laplace transform of y double prime is s squared times capital Y of s minus s times y of 0 minus y prime of 0 plus Laplace transform of y, which is just capital Y of s, equal to 2 over s squared plus 4. Now y of 0 is equal to 0, so this term is 0, and y prime of 0 is also equal to 0, so you're only left with s squared times capital Y of s plus capital Y of s equal to 2 over s squared plus 4. And on the left hand side you take capital Y of s as common factor, and you get this is s squared plus 1 equal to 2 over s squared plus 4. And if you divide both sides for s squared plus 1, get capital Y of s to be 2 over s squared plus 1 times s squared plus 4. So this is the solutions in the frequency domain. Okay. And to find the solutions in the time domain, you apply the inverse Laplace transform. And in this case, you have to use partial fraction decompositions one more time. But in the denominator, you have quadratic factor. Quadratic because this is s to the second power. So to find y of t, we apply the inverse Laplace transform. Of capital Y of s. Alright, that is, you have y of t equal to the inverse Laplace transform of 2 over s squared plus 1 times s squared plus 4. Okay. So again, as I mentioned, we're going to apply the partial fraction decompositions to separate this fraction to two different fractions. So consider 2 over s squared plus 1 times s squared plus 4. And because you have quadratic factors in the denominator, when you write the partial fraction decompositions, this is what you get. So in the denominator, you have the factor s squared plus 1. On the numerator, it has to be a factor, a linear factor, or the factor is 1 less than the one in the denominator. Right, so this is as plus b. Okay. Plus s squared plus 4 in the denominator. Right. So the one on the numerator has to be 1 less than the quadratic factor. That is cs plus d. Okay. Now for this problem, there are 4 numbers that you need to find, right? Capital A, B, C, and D. Very similar procedure in the last example. What you do on the right-hand side, you combine the fraction on the right-hand side, find the common denominator. Eventually, you're going to get rid of the denominator and just look at the numerator. Then you can find the value of A, B, C, and D that way. All right, next we're going to combine the two fractions on the right-hand side. You have 2 over s squared plus 1 times s squared plus 4 equal to as plus b times s squared plus 4 plus cs plus d times s squared plus 1. Altogether divided by s squared plus 1 times s squared plus 4. So denominator is the same, just match the numerator together. So you have 2 equal to, now you're going to distribute and then later combine like terms. So you have as cubed plus 4as plus bs squared plus 4b plus cs to the third power plus cs plus ds squared plus d. Okay. Combine like terms. So you have s cubed as a common factor. You're left with a plus c. You have s squared as a common factor. So you're left with b plus d. S is a common factor. You have 4a plus c. And then you have 4b and d just stay by itself without any s attached to it. So 4b and d by itself. Okay, so 4b plus d. And on the right hand side, on the left hand side, you still have 2. Now to find the value of a, b, c, and d, what you do is you match the coefficients of s, right? So what is the coefficient of s cubed on the left hand side? So you don't see any s cubed on the left hand side, so a plus c has to be equal to 0. You don't see any s squared on the left hand side, so the coefficient b plus d has to be equal to 0 as well. And of course, you don't see any s on the left hand side, so 4a plus c has to be equal to 0. However, you have 4b plus d by itself, right, without any s attached to that. It's going to be equal to 2 because 2 stay by itself without any s. Okay. So that's how you get the value of a, b, c, and d. Okay. So we match the coefficients on both sides of the equations to get. So the first one, a plus c equal to 0, b plus d equal to 0, for a plus c equal to 0, and for b plus d equal to 2. Any questions on this, on how I get this?
No.
Okay. All right, so this is a system of 4 unknowns with 4 equations. Right. You can either use eliminations or substitutions to get the answer. And if you do the calculations correctly, you're going to get this. Let me change this a little bit. So this is equal to 0. So A is equal to 0. B is equal to 2/3. C is equal to 0. And D is equal to negative 2/3. Right, so quite simple. Right. And then going through the partial fraction decompositions, you would be able to separate this fraction into 2 different fractions. For A in this case equal to 0, B is 2/3, C is equal to 0, and D is equal to negative 2/3. Okay. Then the solution is going to be, so y of t is equal to the inverse Laplace transform of as plus b over s squared plus 1. So a is equal to 0, b is equal to 2/3. So 2/3 times 1 over s squared plus 1 minus, or plus, cs plus d over s squared plus 4. C is equal to 0, d is equal to negative 2/3, so that's why you have minus 2/3 times 1 over s squared plus 4. Right. Use linear operations, linear operator properties on the inverse Laplace transform. You get 2/3 times inverse Laplace transform of 1 over s squared plus 1 minus 2/3 times the inverse Laplace transform of 1 over s squared plus 4. Right. So inverse Laplace transform of 1 over s squared plus 1, you go to the Laplace transform table and still look at this formula number 24 here. You have 1 over s squared plus 1. Right. So in this case, b is equal to 1. So inverse Laplace transform of 1 over s squared plus 1 is equal to psi of t. Now for the second inverse Laplace transform, you have 1 over s squared plus 4. Okay, so you suspect that b is going to be equal to 2 because in the denominator you have s squared plus 4 or s squared plus 2 squared. So you have b equal to 2. But on the numerator you don't have 2, so what you do is that you multiply and divide it by 2. So 2 here times 1/2. Okay, and therefore you get this right here. When you apply the inverse Laplace transform, it's going to be psi of 2t, right, with the 1/2 attached to that. Okay, so go back to the note here. So for the first inverse Laplace transform, this is psi of t. For the second inverse Laplace transform, there's a little bit of work that you need to do. So you have 2 over s squared plus 4 times 1/2. Then you can pull the 1/2 out of the inverse Laplace transform operations. And you get 2/3 times psi of t minus 2/3 times 1/2 times inverse Laplace transform of 2 over s squared plus 4. And 2/3 times 1/2, you have 1/3. And the inverse Laplace transform of 2 over s squared plus 4 is going to be psi of 2t. Okay, so that's the solutions of this initial value problem. It's quite a little bit of work, and that is the trade-off that we talked about in the last lecture. When we apply the Laplace transform procedure, that is you have a differential equation in the time domain. You apply the Laplace transform and you turn that into a solution or the equation in the frequency domain, and then you transform it back to the time domain. Yes, it's a little bit of work, but you can handle a lot of more difficult and more strange functions. Okay, so in this case, you handle trigonometric functions, right? In the next 2 lecture notes, when we look at different type of functions or different forcing term, you will see that using the variation of parameters or method of indeterminate coefficients, you're not going to be able to handle the forcing term with discontinuous forcing term or the periodic forcing term. Okay, so that's it for me in terms of inverse Laplace transform, and we're going to move on to the next lecture, which is we're going to find the Laplace transform and just try to understand the Laplace transform of discontinuous functions and periodic functions.